The ways of traditional mobility have been more than beneficial over the past couple hundred years, getting people from point A to point B in half the time. However, there are some things in life that wheels can't satisfy. There have been some modifications to wheels itself on Earth, allowing them to grip the surface of the Earth more durably and reach places most wheels can't. Yet, there have been little to no modifications to the wheels on the Lunar rover. Team Moon Monsters presents the Laser.
Welcome to Moon Monsters Design Day presentation for the Lunar Arachnid Surveillance and Exploration rover. Starting with the back row from left to right, the team members include Nicholas Kapler, Jonathan Kappel, Derek Gilbert, Matt Butler, Simon Lee, Gray Hardy, Justin Lamb, and Manju Singh Espana. The 2022 NASA Big Idea Challenge was to design an unconventional mobility system that can explore the extreme terrain of the moon. Traditional wheeled rovers are restricted by extreme terrain due to high porosity regolith, steep rugged slopes, uneven terrain, and ice. Our solution was to design a six-legged rover that can provide stability through uneven terrain, climb slopes up to 30 degrees, and provide better movement through regolith. The laser is equipped with a LiDAR for obstacle detection, servo motors that provide movement to hips and legs, an accelerometer for stability, and LEDs that light up upon ice detection from the IR camera.
The general system architecture for the laser is shown below. For power to the servos, we have three 6-volt battery packs located in parallel for either side of the laser. That goes to a toggleable switch that goes to a DC to DC converter that provides a constant 5 volts for all the servos on either side and then back down to a uniform ground. Then for the other circuit, we have two 6-volt battery packs located in series that provides 12 volts to the LED lights on the front of the laser through a relay, and then to a DC to DC converter that brings constant 5 volts down to the Raspberry Pi Pico, Raspberry Pi, and any other electronic instruments that require it. The Raspberry Pi Pico and the Raspberry Pi are the two computers on board. The Raspberry Pi Pico is used for a lot of the mechanical movement, such as the data pins to the servos, and the Raspberry Pi is the main computer that we use to culminate all the environmental data, such as LiDAR, accelerometer, and thermal camera.
For our mobility system, we selected a 6-legged, 12-servo motor design, wherein 2 servo motors are attached to each of the 6 horseshoe-shaped hip joints. One is attached underneath the hip joint to provide horizontal mobility, and the second is attached onto the hip joint to provide the leg with vertical mobility. And the leg was based upon a spider's leg design with an initial upward portion and a canted downward portion with a structural strut underneath the knee joint to provide additional stability. Finally, the foot was rounded off and pointed to allow for better mobility and traction over most surfaces.
The instrument located on top of the laser is a RP LiDAR A1M8 LiDAR system. It is a light detection and ranging system that is located on a motor that can measure distances at 1 degree intervals to create a pseudo plane around the laser itself. A frontal pie slice is chosen such that it can measure and detect obstacles up to 12 meters in its trajectory. And if the laser gets too close to an obstacle, it will immediately terminate the walking protocol and start turning in a direction away from the obstacle itself. And once the obstacle is out of its trajectory or out of its line of sight, then it will continue its walking protocol.
For our design, we are using the Adafruit MLX90640 IR camera to be able to differentiate the temperature of our environment. The IR camera compiles an array of temperature readings, and based on that, it corresponds to a color on the color map that we generated. In our case, blue signifies the colder region and red signifies the warmer region. As you can see here, the IR camera does not pick up the Kit Kat or the scissors because it is at room temperature. However, in this image, you can see that the IR camera was able to pick up the ice.
The infrared camera was used to take images to serve as training data for the ice detection model. The model functions off of a binary classification. The image is therefore classified as either containing ice or no ice is present. The model uses a k-nearest neighbor algorithm on the captured image data to classify whether the image contains ice. This type of algorithm was chosen for a combination of its accuracy with binary classification and its simplicity in implementation. If ice is detected by the rover prototype, the 2 front-mounted LEDs will turn on and the rover will stop moving.
So this right here is our accelerometer. The accelerometer is is a device used to measure the motion of an object or the vibrations or anything related to the force exerted on an object that causes it to move. So it could be that the object is moving, it could be vibrations, and it measures everything in 3-axis dimension.
The legs are going to move through servo motors. The servo motors are going to be programmed through a Raspberry Pi Pico. Here shows an animation of how the leg movements will work. This slide shows the hip motors, and we designed the movements to be a point-to-point system. So these points show the motors at a straight position for the hips. Then goes the 2 outside legs will move forward while the middle leg moves back, and then it will swing back and continue to go into a walking movement. The legs have a similar pointwise movement. The 2 red dots represent the legs at a maximum position, or when the rover is standing on its belly. The legs will then go down to a minimum position, or when the rover is standing. These 2 movements can then be combined together to produce a smooth walking movement, with the legs going up and then down as they move from side to side. The way we are controlling this movement is through a Raspberry Pi Pico and programming it through Thonny or MicroPython. The way the code works is establishing the motors through the pins and then establishing their points for the straight, maximum, and minimum positions. These positions are then ran through a while loop to produce that smooth walking movement. The rover will incorporate an accelerometer that will be able to measure the acceleration and the X, Y, and Z direction. There will be times when the rover is at a pitch angle when it is either going up or down the craters. This angle will be around 30 degrees. At this time, it will produce an acceleration in the X direction that should be around 30 degrees. However, if that angle is skewed by some portion, then we need to adjust the motors so that the back and the middle hips will go backwards until that X-axis acceleration is where we want it. A similar scenario is when the rover is walking on an uneven surface. This will produce an acceleration in the Y direction that is skewed from its normal position. One way to counteract this balance is to move the servos that are walking on the elevated surface up more until the rover levels itself out.
Thank you so much for watching our video. I hope you enjoyed it. Special thanks to all of our teachers who helped us along our engineering journey. And here's a special clip of all of our past failures and success in trying to make Call, Haul, and Walk.